Good. So let's continue our lecture. Good. Okay. So last time we talked about Maxwell-Boltzmann velocity distribution, right? And we found that we really want to know what does it looks like of that velocity distribution, right? And then we talked about the fractional number, which is FV, dV, and capital F, capital V, and dV, which is a little bit different between each other. And one of it is velocity, magnitude, speed, and V is vector. This capital V, so this is not capital. It's a bold V is a vector. So it straight tell you the direction straightly. And then we use the concept of the binary collision, because the binary collision has the inverse mirror cases. So because this phenomenon, we can find the formulation of the F need to be satisfied both equation. The first one is because of the mirror cases, and the second one is the conservation of kinetic energy, because two physical limitation or constraint. So we need to satisfy it. So we can understand that it must be looks like A times exponential minus R V dot V. Okay, so they must be look like this. Okay, so this is what we talked about. And then what does that mean? Okay, so then we are going to solve the A and alpha. So what is the alpha and A looks like? And then we need to borrow another concept called total energy. The total energy is 3/2 NKT. All of us know this. And then we're going to see the kinetic theory part. This is kinetic theory part. So every atom's kinetic energy summed up together become 3/2 NKT. So they need to be equal. So you can see that everything, all the atoms has their own velocity distribution, okay? And then half mv squared and times its own probability, okay? And then so this expected value times half mv squared, okay? So then they must be the same. So the equation held, okay? We need to satisfy this. So last time we found that the m here can be rewritten in the form of m because all the velocity of integration from 0 to infinity, which means that also equal to the m, the total number of m, or the total number of the molecular. Okay, so we just transform this green part to here. Right, and then let's continue to write what will it look like. All right, so 4 pi a 0 infinity b to 4 exponential alpha v square dv. Okay, And then, what is the bottom part? I will do some trick. Yes, but without the V4. Then, all right, that's easier. Well, it's not, sorry, it should be not 4 pi a 0, it's 2. It's 2. 2. Okay. Yeah, so that's it. And this is green part we are talking about. Okay. Then, wow, this looks terrible, right? This looks terrible. What can we solve that? Luckily, Appendix D, equation D2, in the textbook tell us if the integration looks like this, the mathematician has done their work. Equal to 1 times 3 times 5, 2m minus 1. So this can be found in the appendix in your textbook. It solves this for you. All right. So appendix D saying that if your integration looks like this, with the m here, the m can be any number. All right. And the integration result can be written in this form. And luckily, it looks to us here n equal to 2. Here n equal to 1. Okay, n equal to 2 and equal to 1. Right. So everything becomes easier when you substitute the formulations here. 3, 2 times 4 times alpha 2 alpha pi half, and then this is 1 over 2 times alpha pi alpha half. Okay, so that's it. Again, the bottom part is total number n. Okay. So now we sort of can see that. Let me take a look. Three KT. 忘记是什么了，我看一下啊。3KTN 除等于3除以Okay, so then we can notice that 3 NKT equal to 3 over 2 alpha. All right. So this it can cancel each other, most of them, and there's something pi it can also cancel, and there's something left is 3 over 2 alpha. Okay, so alpha become m over 2kt. Right. And then if you have alpha, you can say A equal to alpha over I 3 over 2, n equal to m over 2 pi kt 3 over 2. n done. Okay, alpha and A all solved. So, which means that you can substitute A and alpha into A and alpha into the NVDV. So your NVDV looks like this one. Very ugly, but everything is known. Everything is known, can be measured. And if you just draw this NV on the Excel, in the Excel, and you can find that it just looks like that. And if you change the T here, if you substitute T, T1, T2, T3 with a big different number, different values, and then you can see the distribution is changing. So for example, if you have a lower temperature, and which means that your velocity, high velocity become kind of decreased. And if you have a higher temperature, which means that the atom has higher possibility to reach even faster speed. Okay, so that's how the distribution looks like. OK， 好，我们刚刚前面介绍就是有一些做一些前情提要嘛，对不对哈？然后那前情提要就是说我们利用了不同的方式，就利用双碰撞这样子的概念去，还有动能守恒的概念去把它的 F 的形式写出来。那我们现在要解 A 跟阿尔法。那解了 A 跟阿尔法呢，我们就会想说 ，OK， 那怎么样还要怎么样去解它呢？我们可以利用能量，好，这整个 content 这个容器的能量是2/3 NKT， 全部都是这样。那全部的能量是这样子，我们已经知道了。那如果从颗粒的角度来看是什么呢？也就是说，反正它里面就只有这些颗粒嘛，那这些颗粒的动能全部加总起来就是2/3 NKT 咯。所以这边1/2 mv 平方，然后还有每个 v 每一颗的速度，当然就是要靠它的 energy density，就是什么density probability density，密度几率密度函数来去算出来的。好，所以这样子这个等式就成立了。那这时候我们就觉得很难解嘛，但是没关系，我们的 n 呢可以把它写成跟这个很像的东西。因为你可以发现，我们在积分的时候 ，NV 抵 V 从0积到无穷大，你没有乘上任何的东西嘛，哈，你没有乘上任何的 V， 它就是基本上就是从头第一个 atom 算到最低数的 atom， 算到最高数的 atom， 那不就是全部的 atom 的数量吗？在这个容器里面，所以正好这个东西其实就是 N。好，那这时候我们就把 NV 带进去啦，带进去就发现就写成这样的式子。那这个式子很恐怖，很丑，但不用担心。我们在 appendix 的时候呢，第一的时候就是古早的科学家就已经帮你解好了。如果你的式子长这样子的话，你的答案会长这样子。然后这个 n 是可以随便取，就是可以是不同的值这样。那我们就会发现哦，这边的 n 是2，这边的 n 是1，好，就把它写出来啦。那一样，绿色是 n 的意思哈。好，然后接下来呢，就是313就变成这么简单啦。然后我们就发现哦，阿尔法原来是 m/2kt。有了阿尔法 NKT， 阿尔法的话，那我们就可以代入进去忘记写这边了。So we can substitute the alpha here. All right, and then you can get A by using n equal to these things. All right, I'm sorry, I forgot to tell you how do we solve the alpha. How do we solve A? We substitute alpha into this green part, and this green part equal to n, and then so that's the reason why we have n here. All right. 好，刚刚忘记讲到了哈，就是把阿尔法带到这个去，然后这边是绿色嘛，那就等于 n 啊，所以这就相等，你就可以得到 A 是多少。然后 A 带进去，A 跟阿尔法就不对，在这里哈，带到这里。就可以有 NVDV 长相啦，终于写出来了。写出来以后，我们用 Excel 去画的话，你可以回家自己试试看。然后呢，你就会发现，如果你带不同的 T 的值，它就会有不同的形状。然后，如果越高温的话，它就会越摊平，然后也越有机会让 atom 跑到更高的速度。OK，that's it。 So this is Maxwell-Boltzmann speed distribution. And then again, I would like to tell you to make it emphasize here, the number of the molecular is MV/dV, okay? MV/dV in the range of V to V plus dV, small range of velocity. And of course, because the is not vector, so this irrespective of direction. So no direction has been mentioned in this and considered in this function. And FV/dV also irrespective of direction. But now you see this is the fractional number f. Okay, the fractional number. So you can see that. So you can compare a little bit with this. You can see. You can see FV dV. Let me take a look. So you can say FV is actually NV divided by total number of N and divide by dV. So you can imagine that this, yeah. So the I should put here. It's better. All right. So you can imagine that MV/dV is a fractional number, right? And fractional number equal to the FV/dV. So this is the probability density function. So remember that FV is the unit is minus inverse of V. So the inverse of V times V. So you can get the fractional number NV divided by N. All right. So then you can imagine that you can understand the NV/dV and FV/dV's relationship between each other. So this is a fractional number of molecules. So let's plot this value as a function. And then again, we can determine what we learned in the previous page. We know the definition of this one, right? And okay, sorry, I shouldn't draw this. I'm sorry. FV MVN. Yeah, it should be this time. Okay, sorry. Okay. So you can see that this is number and fractional number. Okay, so this is a fractional number. Exactly. So that's how we substitute FV by using NV divided by N. This is fractional. NV divided by N. All right. And then previously in the previous page, we have the definition of mean speed and then root mean square speed and most probable speed. So let's directly substitute what we learned in the previous page. And then, of course, you need to borrow some mathematical technique from Appendix D, D.2 and D.3 to get the result. Okay, and then, well, it's not really important here, but we can, that's how we get the coefficient numbers here. So after you've done that, you can directly obtain the value of A over pi times KT over M square root and this is square root 3, and this is square root 2. For the most probable speed, you just do the differentiation for this and make it equal to 0, and you can get the most probable velocities square root 2. Okay, and then you notice that if you have the normalize it, if you make this is 1, and this is the root mean square speed is 1.225 times of most probable speed. And then for the mean speed is 1.128 times of most probable speed. Okay, so this is kind of interesting. We typically most probable speed. Okay, we had this at the top of the curve with the slope equal to 0, and we normally think this is mean speed. No, this is not mean speed. This is most probable speed. Okay, so this is a little bit interesting. It is kind of different from our first thought. This is Vn, and this is V bar, and this is yeah, and this is V root mean square speed. Okay. Okay. That's it. 好，我们要就是把刚刚的 NV 底 V 算出来以后，我们就可以跟density probability density function 密度几率密度函数扯上关系。那我们的定义就是说啊，这 NV 就是在这个速度之间，你有几颗这样子的速度。那 FV 底 V 则是在这个速度之间，你有多少个比例的颗数是这样，比例的颗数，所以这两个差别只在于一个是真正的颗数，一个是比例。那你就直接乘上 n 就好了嘛，对不对？哈，抱歉，我刚刚没有写得很清楚啊，我就应该说这其实蛮直观的嘛，哈。好，那有了这个东西以后，我们就可以把我们之前在讲 mean speed 啊、root mean square speed 啊，还有 most probable speed 的定义带入，把 FV 取代成1除以 n 乘上 NV，OK， 然后再把之前的式子带入进去，然后当然了，你需要经过一连串的积分，积分完以后，我们就会得到 V bar 呢会是这样子的系数，然后乘上这个，然后 root mean square speed 呢就会是根号3乘上后面这个东西，然后那最高几率的 speed 呢，其实是把那个式子做积分，说不对，微分，微分完以后等于0，就会找到它斜率为的极值啊，哈，这极值。然后呢，算出来以后 Vn 会是根号2。那我们如果今天把它视为1倍的话，我们会发现 root mean square speed 它是 1.225 倍的 Vn， 然后这个是 1.128 倍的 Vn。那这时候我们就可以在这个图上啊，标示出来，把 Vn 就弄上面，因为 Vn 很明显嘛，它就是最高点斜率为0的地方，主要是 Vn。那我们会以为说，哎，这就是平均值哦，不对哦，它不是平均值，它不是平均速率，平均速率反而是在高一点点 1.128 倍的地方，前面一点点，高一点点。然后如果是 root mean square speed 的话，它就会更高一点点，是 1.222 倍。OK， 所以这边跟我们就是瞬间的想法不太一样啊，我们以为它中间这个就是平均哦，不是哦，哈，好，就这样。Next one is a little bit difficult, especially if you just read the textbook without listening my lecture. Okay, a lot of your senior students previous few years, they had big difficulty if they study by themselves, just reading the book, because the book has really limited information for this. Okay, but they will need to be used later. So I try to make this as simple as possible for you. Okay, so I hope you can understand this better. So speed distribution in one direction only. Previously, we have three degree of freedom, right? X, Y, Z. So your V has the direction in all the directions. So it becomes a speed ball, speed sphere, right? But now, because later, we are going to talk about equipartition. Remember that, right? Each X, Y, Z has its own partition of energy. So it will become important in a later chapter. So the reason why we are going to separate this divide them from all three directions into one direction, because the result is useful in chapter 14.6, equipartition of energy. All right. So because energy is equally partitioned respective to 1 degree of freedom. So we need to separate from 3 into 1. Now, so NVDV, we just done that. And in the textbook, it just simply tell us, tell you the result, and then without telling you why. Okay, so this is, makes everyone, just cannot understand what they are talking about. So let's take a look. So we're going to see NVX, dVX looks like. Okay, it must looks like F Vx dVx, right? And then it looks, you can see that there's nothing about sphere anymore. So there's no 4 pi v square anymore. Okay, so this is reasonable, right? 4 pi v squared means that every direction has its own possibility. So the 4 pi v squared stand for that, right? But one direction, there's no 4 pi v squared. This is the first difference. You can see that. So you can see that it must be, looks like a exponential minus alpha Vx squared and dVx. Okay? So the first thing is that this one. Okay, they has fundamental difference of the origin. All right. 好，我们现在开始讲了哈，就是说，接下来我们要看 speed distribution in one direction， 看就是那个速度的分布在一个空间一维上。为什么要讲一维呢？我们之前是讲的三维立体空间 x y z， 所以它所有的方向都有速度。OK， 那时候还记得吗？我们就为了跑所有方向速度，就变成一个速度球，因为每个方向都有速度，所以那个4 pi v square 就是它的表面积，也就是说它所有可能的方向的几率总和这种感觉 ，OK？ 但是现在不一样啊，现在你只要找一个方向。那为什么找一个方向？我刚刚没有翻译到，就是说我们都知道，刚刚之前有讲过，一个 degree of freedom， 一个自由度就会跟一个 energy 固定的能量的值，那叫做 equipartition of energy。我不太会翻译这个，基本上就是等间距吗？哦，反正就是 分得很好，对，一个就是对一个能量的这种数值，就是对一个方向的自由度。那未来我们在做14.6章的时候，正好就要讲这个，那这时候他就会需要这个。但是他的课本上都完全没有讲哦，就只说，哎呀，就是我们算了这个以后，那我们就知道这个是一维的，那谁知道？差很多，好不好？所以学长姐在看这个时候都非常的痛苦，都不知道他在写什么。那所以我这边把它统整出来，希望大家可以看得懂一点。好，那总之我们就开始看。那既然人家前面是 three dimensional，我们刚刚算过了，但是现在只有一维的话，就不是一个球了，它是一个一维的变化，对不对哈？所以它就没有这个球的这个4派 v square 的系数，然后但其他都还是维持一样东西，它还是有一样的性质，那只是这边的 v， 接下来 v 就变成 vx， 就这样。OK。So next we're going to standing on this foundation, and then we are going to solve what does it looks like. All right. And remember that previously we talked about the speed ball every direction. Now we are talking about a plane moving because you can imagine that all the velocity uh all the velocity in every direction. It's a ball, but in one direction only. You can imagine that this is small velocity. This is higher velocity, higher velocity, higher velocity, higher velocity, small velocity, small velocity. So you can see that the increment of the one direction is actually a plane moving rather than a speedball shrinking or growing. All right, so this is the fundamental difference for three-dimensional and one degree of freedom. All right， 这边再翻译一次，就是说啊，刚刚不是说这所有的速度的大小都是靠这个球，你从最小的速度积分到无穷大的速度，就好像是这个球从最小的点变成超级大的球，这样一直积分上去，对不对哈？但是现在一维就不一样了，因为不是一个球在涨，它是一个面在移动。你可以想象它的速度，它是这样子的速度，可以是小的速度，也可以是大的速度，对不对？所以说它就是从小小的点，然后移动，所以它其实是一个面的移动，而不是一个球的移动。OK， next, so we are going to do what we did exactly. Okay, so for v it's all the direction. For vx it's for one direction. Okay, so 4v dv here, and I mean 4 pi v squared, nothing here. Okay, so we just learned that in the previous page. And then total number n. All right, you can see that total number n here, you can see the difference of the integration. 0 to infinity, because you can imagine that it's a ball growing. Okay, and this is a plane moving, so this is negative infinity to infinity. So this is the fundamental difference of the two things. And then total energy formulation is 3 degrees of freedom. And this is 1 degree of freedom. So you see 3 over 2 nkt and half nkt. Okay? And then again, from minus 0 to infinity and minus infinity to infinity. Okay, so let me write it down. It's consider a ball growing, and let's consider a plane moving from negative infinity to positive infinity. All right, and then this is what we learned in the previous few pages in the beginning of this course, right? And this one, we do exactly the same thing. And when we do D1 and D2 appendix, all right? And then you can have alpha equal to MKT, alpha equal to MK, and over to KT, lucky. And here, A become this one, and A become that one. And the difference is half. All right. And then summing that together, your NVX dVX become this one. Okay. And then you can see the difference. Tiny difference. No 4 pi. And this is 3/2 half. And there's no V square. And yeah, that's it. Okay. So in the textbook, they only tell you this and nothing here. Okay, so nobody understand what they are talking about. All right. When I firstly studied this, I also don't understand what it is. So I thought it all through, and then I found out, oh, it's just stuff like this. Okay. 好，那继续讲了哈，就是说前面我们知道这个东西嘛哈，然后接下来我们就要做刚刚我在这节课刚开始的时候，我们不是做这件事情吗？我们就会做一模一样的事情啊，然后只是最大的差别就是我们刚刚讲到的是我们的球是从零积到无穷大，但是因为现在不是一个球了，它是一个面在移动了，所以它是从负无穷大，要考虑所有的速度的话，从负无穷大到正无穷大，所以这就是它最大的差别。Consider ball growing， 就是想现在这只球正在往外长，但是这个是一个墙壁在往前移动、往后移动这样子。OK， 然后呢 ，total energy 就是1 degree freedom， 3 degree freedom， 所以这边的值又不一样了。然后你要重新证明一次，然后一样，这边是1.1、1.2的数学公式，然后算出来答案是这样，然后差别在这里。然后课本上就只给你写这样子，就说啊1 degree freedom 是长这样子。然后我们之前学到的是这个，然后没有人知道他为什么，他也什么都没讲。那当初我在看的时候，我也是非常痛苦，就是他到底在写什么。然后我花了很久的时间才想出，哦，原来是这样子啊。然后算出来答案是这样。OK， 好，那希望大家可以看得懂我在写什么。All right. Okay, so next one, mean free path and collision frequency. Number of particles in the volume. Okay, so we are going to see the mean free path. Mean free path means that the particle bump to next one. Okay, bump to next one. Before that, how long it averagely travel. Okay, so you can imagine that if the mean free path is long, which means that they may spend more time to hit the next. If this is short, which means that it bump quite frequently, so collision frequency will be higher. Okay, so mean free path and collision frequency is kind of coupled together. Okay, so let's consider what is how the collision happened in when a ball traveling. Okay, the ball traveling, our focus is this blue particle, and the blue particle will hit. So let's do the averaging. So during the t times, so averagely this particle is traveling a v bar speed, and then within the t, so within the t, it travel from here to here. Okay, so let's count during this travel how many hit it occurs. Okay, so you can imagine this particle travel through here. The track looks like this, right? So you can imagine that it will hit others only if their neighbor within this cylinder. The cylinder has the 2r radius. Okay, you can see that it's r, this is r. So if the particle is, you can see here, this is the center of the mass of the other neighbor. Okay, the neighbor particle. If the particle is outside, I mean, if this center of mass is higher than the 2r cylinder, which means that it will miss, right? So only the particle inside only the particle inside this cylinder will hit by the blue particles within the time t. Okay, makes sense, right? So let's discuss. Let's calculate the number of the gray particles in the volume. How many particles it hits? Okay, again, this one, n divided by v is the number of molecules okay, per unit volume, and times the volume of cylinder. Okay, so cylinder 2r pi, sorry, 2r squared. Pi is the surface times the v bar t is the height of the cylinder. So such many neighbor it will hit during time t. So mean free path estimate. Okay, I will explain what is estimate later. Okay, so mean free path will looks like estimate. L equal to, so you can imagine that it travel v bar t distance and then such many heat. So mean free path is that such distance divided by the number of heat, right? So that's it. And easy VT, and this is N bar, underbar. And this is, we say this is sigma, all right? We just give a value. Right, so it looks like mean free path is 1 over N underbar sigma. However, we need to say this is not exactly correct. Why? Because what we are going to, what we just looked at is that only the blue bar, a blue particle is traveling. The rest of the gray particle stay the same place, remain the same. So which is not true, right? Actually, all the particle traveled with it averagely with average speed. So actually, all the particle is relatively moving. So this is not exactly correct. So that's the reason why this is estimated. This is estimated. So again, just like what we did before, the real mean free path is actually the estimate thing times a factor. Again, we're going to find what is the factor, the value. And this is really interesting. Okay, this is really interesting. Our textbook say, this factor is, our textbook say this is, the factor is pi a over pi square root. Our textbook said in our textbook. However, if you type this mean free path in the internet, it will tell you the factor is square root. Okay? And I don't know why. So this is actually the relative velocity factor. Okay? So I don't know why the textbook saying this factor. I don't know why. Okay? And actually, I don't believe this. I believe this one because this is a little bit, I mean, more makes sense to me. Okay? So it's okay. All right. So in textbook, it used this value to make collision frequency FC, which means Vm divided by L, something like this. All right. So I don't know. And next page, I will explain this one. Square root 2 come from. All right. So there are two mean free price definition. One is textbook, which I don't quite believe that. I believe this one, and I'll give you next page for this. So which means that I won't ask you to prove this in our exam. Okay, don't worry about this. And then so, but it's okay because even without this factor, we can still know that the L mean free path is proportional to 1 over n bar. No problem, right? And also it's proportional to 1 over p. Why? Because n bar equal to mv equal to p over kt, right? So you can see that this is 1 over p proportional to L. And then I will use this proportional law later. All right. I guess I need to give you 20 minutes break. I will see you 10:11. If you have any questions, just come here. Thank you. Hello，欢迎回来，Welcome back。呃，来聊天好了。最近就觉得有一些体认，就是说，哎，年轻的时候可能觉得说，啊，这样子这样的状况啊，忍一忍就过去了，没有差这样。那然后越来越中年以后，就会觉得说，好像越来越无法忍受这些东西。嗯，可能是因为身体不再强健，所以说，就例如说啦，椅子如果稍微高一点点，或是桌子稍微高一点点，以前就觉得没差啊，念书从来没有在管这件事情，就坐下来念书、做事情、打电脑都可以。但是现在啊，只要座椅稍微高一点或低一点，我就会浑身不舒服，然后就开始腰痛背痛这样，所以我就真的还蛮夸张的。所以以前不用升降桌都可以念书念得很好啊，或硕士做得很好。可是现在就是只要一个1公分、2公分这样，然后我就去调啊，调到很好。所以现在我买了一个新的升降桌，超棒的啊！这个升降桌它可以低到这么低呢，这么低耶。然后我一直都觉得以前啊，就是应该说最近越来越觉得，因为我身高不高，所以平常这种一般设计的桌子都太高了，所以我每次在打字的时候，我的肩膀都会耸起来，然后去 fit 这个高度。但是现在把它弄到很低以后，我觉得打字好舒服哦。然后昨天我就花了大概5分钟在那边细调我最喜欢的那种高低的那种状况，然后觉得以前根本不需要这件事情，但是现在就觉得差1公分都会觉得让我很不舒服所以我就在想，诶，对，就是还蛮有趣的，就以前都没差，现在就差一点都会差很多这样。呃呃，但是啊，对于别人或是小孩子好了，因为小孩子有磨练我，就是说遇到人在犯一些错的时候，我就会比较有耐心。那所以等于是说，以前很没耐心的人，现在变得稍微比较有耐心一点。但以前对于自己身体的，就是那种就是那种小不舒服，觉得没差的，然后到现在就开始有差，所以一切都是一个交错的一个成长方式。这时候就让我想到，就是我不知道在哪里听到就是你知道剧情啊剧情电影的剧情通常都是一个交错的方式，就很简单就例如说像复仇者联盟里面的那个钢铁人跟那个美国队长对不对？他一开始钢铁人是比较就是不听话的，然后美国队长是很听话的，一开始的时候，但是到后面越来越发生一些事情，让美国队长反而是要叛逃，就是要把神盾局就是就是反而是 against 神盾局的，然后反而钢铁人就开始要签署那个条约，我不知道大家有没有看过，所以就是他们都是一个交错式的。那现在发现好像人生真的是这样子，就是人一直都会有矫枉过正的状态，然后现实就会给你一个反击，让你到另外一个极端。所以我就觉得真的是蛮有趣的。然后物理也是振幅都是超过就是然后又把你板正到超过，然后这样子这到最后回归到一个你最舒服的状态。所以我觉得有时候人真的还蛮有趣的人生真的还蛮有趣的。呃，越活越老，就觉得越有一些感触。当然我知道大家听到这个完全没有感觉，因为我小时候听到老师讲这些完全没有感觉。但是就请他，搞不好有听到这件事情，然后你以后跟我一样老的时候， 你可能就会想，哦，原来做人 D 那时候遇到这样的状况，跟我一样的，这样大家都逃不掉的，好，放心吧。Just talk about my endurance of my physics and my endurance of my mentality. It's kind of swap the position. When I was young, my physics endurance is okay. Tolerance is okay. But now my physical tolerance decreased badly. And my mental endurance, something like uh, I can tolerance others mistakes better than I was when I was young. So I think it's kind of swapping the position of mental and the physical uh uh yeah of myself. Yes. Interesting life. All right, so let's continue. I also want to say thank you to the service in 7-Eleven. When I was there, it was 3 past 10, and there's a long queue. There was a long queue. And I found that maybe I cannot make it, but the service in 7-Eleven just consumed all the long queue within 3 minutes. They are really efficient. So Taiwanese service is kind of top of the world. When you if you just been to if you've been to other like foreign country like US, UK, European, their service is good, but really slow, really not really efficient compared to Taiwan. So Taiwan is really good. 听得懂吧？哈，7-Eleven 的员工实在是太厉害了哦，这是世界第一，我觉得。超长的 Q 是 L 型的哦。我那时候10点3分去那边想要买咖啡，就看到啊，我要不要放弃呢？我想要赌一把好了。结果他在5分钟之内把全部的 L 型的就轮到我嘞，然后就买咖啡又好了，然后走回来刚好，哇，真的是太了不起。好，All right, so let's continue. I spent 8 minutes to right. So I think I haven't done the translation here, right? So 好，就是说我们要讲是平均自由路径，那什么意思呢？还有碰撞频率，其实就是在撞到下一个之前，平均它会走多远的意思。那要怎么算呢？我们就来看主角在这里，然后它以平均的速度往前走 t 的时间的距离哈 ，v bar t 的距离，那它撞多少次呢？那就要看这个路径中它会撞多少次啊？要怎么去算？就是说啊哈，以它们的直心来看，这个直心正好在这个2倍的 r 的距离的地方画一个区域。为什么呢？因为如果这个直心啊在上面一点点的话，它冲过去它就不会碰到它啦啊，所以说它就是在这一个区域里面的直心在这个区域里面的 particle 它才碰到。那这个区域有多少颗呢？一样 n 除以 v 乘上 volume， 这样就好了。OK， 然后那我们就算嘛，它走这么远，然后撞了这么多颗哦，然后就是它的平均没有撞到的距离是多少？好，然后我们取个名字，这是 n 底 bar， 然后这个东西叫做 sigma， 好，这个不重要。那但是我们发现这边多了一个叫做 estimate， 就是粗估的、概估的，这其实不是完全正确的哦。原因是因为我们认为这个 particle 灰色的 particle 是我们在算的时候，假设它是留在那里面，它是不会动的，任由蓝色去撞它。但实际上不对，实际上它也在动啊。所以理论上来讲，应该要乘上一个 factor， 乘上一个系数来修正它。又来了，我们要修正它。但是呢，修正它要怎么修正？是因为要朝着它，就是灰色它也在相对的运动的状态下来修正。结果课本上却说它的修正系数是根号8除以派 却也没跟我们讲为什么。然后他就拿这个东西，然后去来算 collision frequency。好，我实际上是不太懂课本上为什么这样写。那而且你去上网去查 mean free path， 它其实是根号2。啊，我不太懂，不过没关系，课本上写就这样写，那我不会考这种东西。那总之我就跟大家讲，就是它跟这个东西有关就对了。好，这个 E 除以 n 底 bar sigma 有关。好，那 n 底 bar 又跟谁有关呢？n 底 bar 就是 n 除以 v 嘛，又是 p 除以 kt 嘛，哈，所以说 L 是跟正比于 E 除以 p 的。好，等一下我们就关注这件事情就好了哈。L 是正比于 one over p 这件事情。那等一下我们会用到。那下一页我会补充说明，就是为什么是根号2。Okay, so next page I will do the supplementary material supporting data for square root 2 factor. Okay, next here is supporting information info. All right, so I want to let you know why this is square root 2. So V1 is, so we use vector V1 with the arrow bar to make it easier for me to write, all right? And the other is V2. We're using arrow to represent the velocity, to vector, okay? So this is V2. So this is, we're using random molecular velocities. All right. So we are going to get V relative or relative velocity, which is V1 minus V2. Previously, we assumed one of them are stuck there, and then V1 just hit that, but no, it should be V1, V2. And so velocity of a relative is V1 minus V2. Okay, no problem. So V relative value, it should be V relative dot V relative. So the value of the V relative, it should be dotted and do the square root. All right. So V1 minus V2 dot V1 minus V2 dot. All right. Okay. This should be minus. All right. So it becomes okay. V1 dot V1 minus 2 V1 dot V2 plus V2 dot V2. All right. And then, so this is one particle. Sorry, a pair of particles, 2 particles. How about average? Average relative velocity. How about average then? Average, we give them a bar over. Okay, and I will do a trick again. Copy and paste. All right, and I will give it a bar above. Okay, and Interestingly, V1 dot V2 average together, right? And because V1 and V2 has all the possible direction, and they are equally probable, right? The same probability. So when they dot together and do the summation and then divide by their own numbers, all the average should be 0 because everyone has the same chance because they are random, so they canceling each other. All right. Then it becomes V1 squared plus V2 squared bar. All right. And again, they are random, right? V1 squared, V1 average, V2 average, because they are random. So the average V1, V2 should be equal. Okay. So we can just write it out V bar. So it becomes square root 2 V. So that's the reason why we have square root 2. All right, in the previous page. 好，我们要讲就是补充资料啊，为什么它是根号2？根号2其实就是我们要讲就是两个 particle V1 V2，然后我们这边写不要写出题啊，好累哦哈，所以我们把它加了一个箭头在上面，而且它们是 random 的2颗在 container 里面容器里面，它们之间的相对速度就是 V1 减 V2 吧，哈，没有问题。前面的话是我们的 V2 是0，那这样是假的，然后是错的哦，不对，我们要 V1 减 V2 才是真正的相对速度。好啦，那相对速度这个是向量，那我们要算它的值是多少？这值是多少，我们就 dot 它开根号，所以长这样子。好，长这样子以后展开就变成这样子。好，这是2颗，可是我们要算的是平均整个 container 里面的容器里面的平均速度，平均相对速度。好，那怎么样平均呢？啊，所有东西都平均就好啦，哈。好，那平均起来，我们来一个一个看。这边中间 V1 打 V2，它是你可以想象 V1 打 V2 是可能随便去挑2个，再随便再加上其他2个，再其他2个，全部加它的结果全部加总起来，你会想象它的 dot 可能是正的，也可能是负的，对不对哈？那而且都是相同的平均，就是都一样的几率，所以他们的选择的几率是完全一样的，所以你平均下来，他们会相消掉，有正的有负的，全部会消掉，会等于0。好，中间这样等于0以后呢，我们再看 V1 打 V2，V1 打 V1 跟 V2 打 V2 的平均。那一样啊 ，V1 跟 V2 平均起来，它们没有任何的区别啊，它们的平均会是相同的，所以就变成根号2了。OK， 好，就这样。Next one. So we just learned the mean-free path. Let's correlate the mean-free path with probability function Px. So you can see mean-free path means that it doesn't hit before next collision, right? Next bumping. So let's see how is the probability correlated to mean-free path. So let's take a look. The probability that the molecule will travel x direction before collision. It sounds really similar to mean-free path, but this is probability. So you can imagine that has higher x means lower p, right? Higher x means lower p, right? So yeah. And then we want to see what is px looks like, okay? But if we want to see what px looks like, we need to add in many kind of physical concept, many physical constraint to help us to solve the px. Okay, so we will introduce another coefficient called alpha. Alpha dx alpha times dx means that the probability that a collision will occur in dx, okay, they will bump to each other within dx. Okay, we kind of using two approach, this approach and the other approach, to make them connected and try to solve it. So that's what we're going to do in the next few minutes. Okay, so let's take a look. So probability that not hit on any molecules in the distance. So you can, in the distance x, okay, so if it travel x and it not bump to each other, so their probability is px. No problem, right? This is simple. Now, let's consider when it travel x and then extra dx, extra small dx, they are not bumping to other is 1 minus alpha dx. The alpha dx is, it will bump to others. Okay, so 1 minus alpha dx is not bumping to others. So px after they travel successfully x without bumping to others. And then one more dx, they are not bumping to others, probability is 1 minus alpha dx. Okay, so you can see this. And interestingly, if px is always correct, actually the uppercase will be equal to next the bottom square rectangle. Px plus dx is the probability not bumping to others in x plus dx direction distance. So basically, those things should be the same. All right. So we can say px plus dx should be equal to x e minus alpha dx times, okay, px times 1 minus alpha dx. Okay. So yeah. And then we can see that if we just expand it and make this one using Taylor series expansion, you can see that a plus h, x plus dx, okay, equal to fa differentiation times h, and blah, 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 blah. This one are these things. These things are high order term. High order term can be neglected because you can see that it will divide by 2 factorial, n factorial, and also a lot of higher order differentiation. So they can be neglected. So here equal to this one. Okay, so you see px plus px1 times h is dx. All right, so this one equal to this one. All right. Now, the px is a differentiation equal to minus alpha px. Okay, that's it. So now you can see that, oh, there is a function called p. After its differentiation, it obtains itself and then times a coefficient. So p must looks like a exponential because exponential differentiate by itself is exponential itself, right? So again, px need to be looks like a times exponential minus alpha x. So you see, that's it. Now let's define a and alpha. Try our best. Okay. So this is ODE, ordinary differentiation equation. Okay. So it can help. After we took the course of mathematics engineering mathematics, right? 公式. So we just apply the boundary condition. What is the boundary condition? You see, obviously, E0 equal to 1. Why? Because no travel, no heat, right? Probability that a molecule will travel x before a collision. If there's no travel, 100% you won't collide. 100% you won't bump to others, right? No travel, no heat. 1. So after you substitute 0 to x, can get a equal to 1. All right, so p equal to exponential minus alpha x. We done that. We found that. 好，我们要讲什么呢 ？mean free path 跟几率函数 p 的关系。那应该说 mean free path 是这样的。那我们要看的是不要撞到别人的几率有多少。OK， 它是平均嘛，但是我们是要看的是他们一定会有关系。好，因为它的期望值会等于它嘛，对不对？哈，好，有关系。那我们来看 p。那 p 的话呢，就是说它这个函数走 x 的距离，它不会撞到别人的几率是 p。那但是有这样子，我们还是算不出来啊。我们要找就是其他的方向去帮助我们去解它。那我们就算一个嘛。好，如果今天我们走了一个微小的距离，它会撞到别人的几率是阿尔法哦。好，我们就是等于是用另外一个方式去 approach 去试图去解它这个事，等于说两边要把它连在一起，就可以帮它就可以解这个东西。所以我们就另外引入了一个阿尔法 dx， 是它会撞到的哦。在这个 dx 里面走的时候，它会有这样阿尔法 dx 的几率会撞到它，撞到别人。好，那这时候我们就来看一下，我们来试图把它结合在一起。我们走了 x 以后，它不会撞到是 px 的机会。那如果再多走 dx 呢，就会是1减阿尔法 dx 的机会。好，这两个乘在一起，其实就会相等于它直接从 t 走 x 加 dx 的距离的几率。所以这两个东西是相等的。它要满足这边，又要满足这边，它们的几率是相乘嘛，对不对哈？所以说 px 加 dx 它的乘会等于 px 乘上1减阿尔法 dx。经过一些代换跟泰勒展开，去除掉高阶项以后，我们就会发现底 px 就是 px 的微分会等于负阿尔法 px， 也就是说这个函数必须要长得跟 ex 很像。为什么呢？因为 ex 做微分的时候会长成它自己。所以呢，它既然微分长它自己，它一定会长以 exponential 的长相，所以它的系数一定是负阿尔法，因为它这样微分以后它才跑到前面去。OK， 那一定有一个常数嘛，因为它这边可以有任何常数长得这样，不一定啦哈。所以呢，这 a 还要待定。那我们有 ODE 的常识，在公式里面学到，要解它呢，只带边界条件就好。边界条件通常都是很极端的值，我 x 等于0的话，好，那0的话带进去会怎么样呢？我们知道它的值是不往前走，当然就不会撞到任何东西嘛，对不对哈？所以说几率不撞到的几率为1，就可以得到 a 等于1。OK， next， so now let's talk about how we correlate the p to mean free path L. How can we correlate it? Remember that if we are going to correlating the mean things and probability things, how do we connect by them? We're using probability density functions here, probability density function, right? Because this is probability density, right? Density. And if you have probability density function, how can you connect this to L? How can you connect to that? By using what value? Anyone? Bonus and gift. What should I say? How to connect probability density function to the average value by using what value method? Anyone? We've done that many times. Theory learned from in senior high school. Anyone? Start from by E. Anyone? Bonus and gift. Come on, come on. Anyone? Hint. E. Start by E. Initial by E. E 开头的答案。什么值啊？我讲的好明显。Come on， 来，嘿，请说。哎，不是，是值 x。Anyone connecting probability density to the average value, mean value？ 还记得这个东西吗？一开头，答案都已经写上去了。Anyone？ OK， 期望值很好 ，expected value，right？ 好，你可以来这边写你的号码跟你一个奖状，不是奖品，不是奖状。Right, expected value. Connected by expected value. OK， 可以来写下数字，然后拿奖品，谢谢 ，Thank you. Right, so we need to connect probability density function to expected value. I mean, connecting to the mean value by using expected value method. OK， 可以写一下在这里好了。谢谢。好，谢谢。然后请选择你的礼物，然后你可以告诉我你选了些什么，我还蛮有兴趣的。All right。啊 ？NSYSU， 我记得是一个大学。NSYSU 中原吗 ？NSYSU 是什么？反正我之前去过太多地方去演讲，所以我会走散啊。NSYSU 这边有同学是从 NSYSU 毕业的吗？没有。这是什么？你知道吗？喷，对，那个酒精，对，好，谢谢。果然是有用。我发现里面有一些东西绝对不会被选到的，例如说2023的桌历过了，2024的桌历也过，也几乎快过了，所以应该没有人会选。可能就这样真的要把它丢掉。好，谢谢。Right, let's continue our lecture. So we need to connecting L with P, the probability function. The link is probability density function. So probability density function fx. So you can imagine that the P is the by definition, probability density function should be fx dx integration equal to p. So fx is also the dpx, the differentiation of the p. So it should be alpha exponential minus alpha x. Okay. Maybe you don't understand why there's no alpha minus because the probability won't have negative value, right? So we're just adding absolute value here. Okay. Now, so the mean free path L will be the average x, because x is the distance that it won't be hit, right? So x times fx dx from 0 to infinity. So you do the differential integration here, you got 1 over alpha. Okay, so it helps us to determine alpha is actually dx equal to exponential minus x. L, mean free path, is actually the inverse of alpha. Everything connects together. Okay, so x. All right. So if you draw this px and you draw the xl, the xl is here. Okay, xl. So if your x is L, just become 1, right? So your mean free path is here, 1. So if your mean free path, if you travel mean free path distance, you won't hit others. The chance of the probability that you won't hit others when you travel mean free path distance, you only have 33% of survival. So even this is mean free path, you travel mean free path distance, you still only has 33% not bump into others chance. Okay? 好，这样。So you can see that px, initial number of particle in the molecular beam, the number of particle remaining in the after distance. Okay, so you can see that the px is actually equal to n over unknown. What does that mean? The n here is number of particles remaining in the beam after the distance x, which means that why it will stay, because it doesn't bump to others, right? So it will stay. Unknown is all the particles in the previous, before the bumping. After it travel L, and you will find that 37% will stay in the beam without bump it. If it bump it, it will go out. But if it doesn't bump it to it, so it will stay. So 37% of particle will stay in the cylinder, but the rest of 63% particle will hit outside of the cylinder. All right, so this is called survival equation. 37% survive in the cylinder. OK， 好，要讲的是 survival equation， 存活下来的方程式。那我们刚刚其实还没有讲完，我们的 px 呢要怎么样？我们 px 还有一个 alpha 还待定，对不对哈？那我们也知道 px 一定跟 L 有关系，L 就是 mean free path，对不对哈？ 那我们要怎么样去用几率连接到那个命的这种东西，就是平均的这种东西呢？我们之前已经讲了很多遍了，我们使用了 probability density function， 也就是说我们要先把 p 转换成 f， 然后 f 呢再去积分它们该有的值平均，才可以得到平均值。这个方法我们就使用的是期望值的方法，对不对？好，这是我们刚刚问到的。好，那所以说我们的 probability function 要先把它转成 f， 那这 f 的定义就是 f 积分以后会得到 p 嘛，对不对？好，那这样仔细比较起来，我们就会发现 f(x) 其实就是 p 的微分咯。好，那 p 的微分，我们这边加一个绝对值，为什么？因为我们微分以后，我们都会得到一个负阿尔法，但是问题是我们的几率是没有负的，所以我们把它加一个绝对值吧，噔噔就变成这样子啦。OK， 然后接下来呢，我们有的 f(x) 我们要去做期望值，也就是说 x 跟 f(x)， 也就是它不会去碰到它的几率是多少。期望它不会 travel x， 然后不会被撞到的平均值就会是这样子的显现出来，就 x 乘上它的几率密度，然后再做积分，就会是 x bar。那这 x bar 它不就是 mean free path 吗？然后只有积分下来得到是1除以 alpha， 我们就发现哦 alpha 其实是 L 的导数呢，所以我们的 alpha 也算出来了，所以我们的 px 确立了，就是这样子。OK， 好，得到这个式子以后呢，拿一趟干嘛的？我们来看哦，就是它是跑了 x 以后，它不被撞到的几率是多少？那这样是不是可以想象，就是说我们这个球啊，在这个 cylinder 里面冲过去，那冲过去的时候呢，如果它撞到了，它就会飞走，飞走，飞走；如果它没有撞到，它就会留在原本的地方。那也就是说啊，即使如果你今天用这个图来做图 ，XL 来做图，这如果是 X 就是 L 的时候，它就是1嘛。这个如果是1的话，它得到的值是 0.37， 什么意思呢？就是这个 particle 呢走了 L， 它会有37% 的几率不会撞到别人，有67% 的几率，63% 的几率会撞到别人。好，所以没有被撞到的有37%，没有被撞到就留在原本的地方，我们叫它 survive， 存活下来了。好，大概是这样子。Right, so next, let's continue effusion. Effusion, the gas leak through the small pore and the equilibrium state of the gas in the container will not be appreciably affected. 什么意思？Sorry, what does that mean? Effusion means that it's a small leakage of the container, and the leakage, the hole is so small that even they leak, but the whole system kind of neglected, ignored that effect. Okay, so small. So you can imagine this is so small. And then the question is that how small is small? Okay, so the area of the hole is a diameter d, pi d squared over 4 is the area, right? The area. Right, so pi d squared, pi d squared divided by 4 is the area of the hole, right? Needs to be much less than 4 pi L squared. What is 4 pi L squared? Remember that this is a sphere area. So compared to the entire surface area, the hole needs to be much less than that. The area of the hole needs to be much less than the entire surface area of the sphere. Okay, so d squared less than 16L2, of course, right? And after that, how can we interpret this much less than? Much less than can be, let's say, 100. How about that? 100 times. We consider that much smaller. So here, d squared less than 0.16 L squared. And equal d need to be, the diameter of the hole need to be less than 0.4 L. So you can imagine that, sorry, I forgot to tell you what is L. L is the mean free path. So you can imagine that if this particle travel L, okay, distance, if the L, which means mean free path, beyond the mean free path, if the particle is here and travel greater than L, typically, averagely, it won't touch the area because they will bump to others and change the direction. Okay, so that's the reason why we choose L. Okay, so the L travels such long distance, atom such L distance. So if it meet it, and then it go out, right? So the L is the scale that we care about, because this is the average atom travel distance. All right. So that's the reason why we use L to estimate the scale of the D. So the D need to be less than 0.4 L. Okay. So but this is not easy to satisfy. This condition is not easy to satisfy. So greater L is easier for D to be satisfied, right? So T needs to be small. Remember that I just asked you to use this page 25, right? And we're using the L is proportional to 1 over P. And so greater L is easier for effusion. So greater L means smaller P. So effusion is a low pressure phenomenon. Effusion can only be found in low pressure. So if you are going to activate effusion, if you want to make the atom do the effusion out of it, but not affect the entire equilibrium, you need to make it really low pressure. That's the conclusion. So for an ideal gas, so effusion is actually a low pressure phenomenon. And for ideal gas, m bar over n divided v p over kT. So the molecular flux, which means that atom will touch the area, right? We just learned that 1 over 4 n v squared. Sorry, n bar v bar. So, and also we know that the v bar here. Okay. And we know that v bar equal to 8 kT over Im divided by half, right? We know that. So we can know that the molecular flux is P divided by 2 pi m kT. All right. So if we substitute this here, and we can get this one. All right, and m bar EKT. Okay, so now this is the result, and then we found that we want to particle hit this, so which means that we need to make it higher, phi. So n need to be small to increase the molecular flux. So which means that the lighter and the faster. So the lighter atom has higher probability to initiate diffusion. So that's the reason why if we want to separate U235 and U238, we can just using this method to separate them, because 23A and 235 has lighter mass, so it has higher probability to go out of the system. Okay, so that's the conclusion. Sorry, I make it 2 minutes delayed. I will see you after 10 minutes. I will start my lecture 12 past 11. Thank you. Okay, welcome back. So, translation, right? Effusion, 中文怎么翻啊？泄漏吗？哦，那就是它气体的泄漏在一个非常小的洞，那这个洞呢，它小到就是说，就算流出去，它的这整个系统的状态并不会有太大的改变。那我们这时候就要想说，什么叫做小？我们要定义什么叫做小？那小的意思就是说，这个对 particle 来，对于 particle 来说，它会跑到那个洞的这边，跑到这个洞这边。那什么叫做跑到洞这边？就表示说跟你的平的 mean free path 一定有关。因为如果你今天不是用这个值的话，你是用例如说更大值，它表示说它还没跑到，可能就会撞到别人就跑掉了，对吧？那所以说 L 就是一个它来粗估这个 particle 的行动的能力跟它的动的大小有关，这样子。好，那什么叫做小呢？也就是说，它这个 particle 呢，在运动范围之内，运动范围之内的这个球状的面积来说，这个洞的面积占比非常的小。好，那也就是说，我们的洞的面积要远小于以 mean free path 画出来的球面积还要远小于它。好，那这时候我们就把它算一算，就发现哦，它的 d 要远小于16L 平方。那我们要怎么样去看什么叫做远小于呢？那我们就给它乘100倍，好啊，我们就给它100倍，就发现它达到这样的答案，我们就知道哦，d 要d 要小于0.4L 才叫做小，啊，才叫做小，才在我们定义中叫做小。那这时候我们就会发现 L 乘上0.4就是要大于 d，那我们刚刚又知道 L 是1除以 P 的，就跟它成正比。哦，在25页的时候有讲到。那要满足这个条件其实很难呢，所以呢，我们要尽可能的让 L 变大，才会让这个现象发生。那这个要如何让它变大呢？就是要让 P 变小。所以说 effusion 这个是低压的现象才会容易出现。好，那这时候我们再继续看下去，也就是说，我们要让这个球呢真正撞到这个洞，是要看它那个通量啊，对不对？哈，那个通量之前我们学过了，N 我们也知道了，V bar 我们也知道了，所以我们把这个东西写出来变这样子。好，也就是说呢，我们要让它碰到这个地方，要怎么做呢？要怎么样？应该说让它提高这个几率呢？让它提高它的通量呢？可以看到，除了刚刚 P 已经定了，没办法了以外，那我们要看 M。如果在相同的温度下，在同一个材料被混在一个容器里面，在相同的温度下，要看它们的通量，就只有改变它的质量。所以说我们会发现，更轻的、更小质量的，它会有更高的通量。OK，那所以我们就说，我们在U235跟 U238之间，要怎么样分离它呢？我们因为它们就差体的重量嘛，所以它可以用这样子的方式去让它泄露出去，来把它分离掉。这就是之前的科学家用的东西。Alright, so next, mean speed of escaping molecules. Basically, this is really similar to what we learned in the previous page. Just imagine that there's a hole and the particle escaped from that hole, which means that it go through that hole. So it's all related to the flux, right? Go out of that hole. So the number of molecules with speed here. So we are going to see that what kind of speed usually is to make the particle escaped from that hole. So we are going to get expected value again. Okay, so 5v dv this flux times its own velocity expected value. So you see mean speed of escaping molecular to make it escape, to penetrate, to go out of that holes times its own velocity. Again, you need to make it ratio. You need to make it probability, right? So this is the value, and this is the entire velocity integration. So let's make it probability. So entire thing is expected value again. All right. So if we summon now Maxwell, if we substitute this to here, we can obtain that. Again, this is ugly, but we will try our best. 0 and v4 exponential minus m v square divided by 2 kt dv. Okay, and again, this is similar, but a little bit different, and which is different from that is 3. It's 3. All right, so everything's the same. Yes. Okay, again, appendix D is your good friends, and it will make it 3/4 4 pi kt divided by m. Okay, and 1/2 equal to 1.1 AV bar. Okay, and remember that V bar is 1.5696 kt m square. All right, so this is for your information. All right, and then you can notice that so escape V bar is greater than V. So if you want to escape from the container, you need to run faster than others. That's the, that's the way it is. The faster molecules have greater probability of finding that hole and escape. Right. 好，最后一张就是说，最后一张投影片就是说啊，我们要算的是跑出去这个洞的分子，它的平均速度会是多少？那跑出去就跟我们的通量有关了，对不对？哈，这通量有关。这通量还记得吗？这通量这个会 dV 会跟它的速度有关系，所以呢，我们必须要把这个速度做积分。你看，这也是期望值啊，但是你这个 v 乘上这个 dV 以后，5v dV 以后，还要再除以它的全部的速度积分，这样它才会是一个几率嘛，对不对哈？然后再乘上它的 v。好，那这样算出来做积分很难。Appendix D 可以帮助我们算出来，算的答案是这样，然后它答案是 1.18 v over bar。那这个 v bar 其实就是这个值，但是也是我们的平均速度。也就是说，如果你要平均起来，你要跑出去的话，你平均的速度要比一般的平均速度还要多 1.18 倍。也就是说，你跑得越快，你越容易发现那个洞，越容易跑出去。OK， 基本上还蛮合理的。好，就这样。So I just finished the PDF 4, and then we are going to explain PDF 5. And now PDF 5, we officially enter statistical thermodynamics, which is great. We're going to entering the next chapter. Kinetic energy is sort of pre-knowledge before we entering statistical thermodynamics. And when we study statistical thermodynamics, we need to learn quantum mechanics, borrow quantum mechanics techniques to help us to explain things. So this is PDF 4. Now PDF 5 is statistical thermodynamics. Let's begin. So now statistical thermodynamics. Go. History. Thermodynamics is the study of energy and its transformation. No problem. Consider progress. And then we found that classical thermodynamics is a powerful law. Good. But zero molecular inside. No particle, no molecular, no atoms concepts inside. So statistical thermodynamics need to fill that gap. Okay, fill what gap? Zero molecular inside. We need to fix it. We need to fix it. So that's the reason why we need statistical thermodynamics. The developed microscopic property. What? Properties. Okay, to already well established macroscopic behavior. What does that mean? Basically, just connecting what we see and what it behaves underneath. Okay. More simply put, statistical thermodynamics relates the average, because entire whole behavior is actually all the average behavior of the underneath smaller scale. Just like our brain, our decision, what we see, our emotion is actually controlled by our brain. Our brain chemicals, atoms, things translating will affect what we behave. Okay, so the average of all the small stuff in our head, average then, and we can act while you see our behavior. So this is really, people are really similar to the material. We are matter in the world, right? In the universe, really similar, right? So average of molecular property, so it becomes the bulk property or classical properties that we see. So the pressure, temperature, and enthalpy, everything is all related to small scale atoms, the average of them. So a particle theory to interpret equilibrium property of macroscopic system. So yeah, we learn particle things. And luckily, after we do the average of the particle, they are really similar. They matched equilibrium property of large scale quite well. That's surprisingly good. 好，我要讲的就是传统热力学是没有任何的分子啊、原子的概念。那实际上，为了要足这个缺失，统计热力学就是要把分子、原子的性质平均起来。结果没想到，竟然可以跟巨观的性质完全相吻合。那等于是说，不同的方法得到相同的答案，你就可以知道，这样的东西绝对是对的。那所以说啊，统计热力学就是你的颗粒的理论去解释巨观的稳定的现象怎么来的。OK， 蛮厉害的一个东西。 So now we are going to borrow quantum mechanics. Okay, quantum mechanics provide a foundational principle for molecular process because molecule is so small, so they are not 100% obey the physics we saw in a large scale. They behave quantum mechanically. Okay, so molecular statics mechanics need to use the quantum mechanics. So we will develop that by using molecular context. And you see, molecular behave quantum mechanically. So we need that techniques, need that, math and skills. However, this is not a scope in our lecture. I'm not expert in quantum mechanics. This is really difficult for me. I don't know. So we just use that. I just use that. So we can discuss if you have questions, but maybe I cannot give you a 100% good answer for quantum mechanics. All right, we just use that. 啊，要讲的是量子力学。那可能会觉得很奇怪，为什么要学量子力学？那是因为我们要讨论的是分子的现象。分子的现象它必须用到量子力学，因为它的行为太小了，它可能跟我们一般的牛顿的传统力学是不太一样的。那我们要去用它的一些数学公式跟例子，但是我不是专家哦，所以如果今天你对这个东西有问题，你可以来跟我讨论，但我可能没办法给你100分的答案哦。那我尽力而为这样。Next one. Now, energy is quantized. Quantized. What does that mean? Quantized means that it is not continuous. Not continuous. It's having step. Okay. Imagine that your coffee have a certain can only have certain temperatures. So normally we saw that our temperature is kind of continuous. 25 degree, 25.2, 25.25678, blah 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 blah. So this it looks as it's a continuous. So when you plot the continuous temperature versus time, you look like a continuous line for the coffee. By the way, for me, Ely coffee is the best for me. I don't know. How about that? If you have, you can recommend me other coffees, which is, I think Ely coffee is quite nice. And it's really interesting. When I travel to Italy, and every coffee in every shop on the street, on the, in the countryside, their coffees are really, really good. So yeah, I don't know why they're cheap and good. So I really enjoy drinking espresso in Italy. Very nice. 我讲的就是那个意大利的咖啡真的是好喝哎，就是我刚刚说啊，伊利有是就是我觉得很好喝啊什么什么，那它当然是意大利的。然后我之前去过意大利，路边的那种小摊贩啊，乡间随便一间咖啡店的那 espresso 都超好喝的，了不起哦，不愧是意大利，就这样。那可以去喝喝看那边的咖啡，真的厉害。那好讲OK，I continue. So the macro scale temperature decrease continuously. Look by our respect in our eyes, but actually their temperature is actually stepped, is quantized. It's not continuous, okay? Because they have energy level. All right. So imagine that actually macroscopy looks continuous, but in microscopy, the molecular getting cold, it is stepwise rather than continuous. Okay. The reason why we see macroscopy is continuous because the spacing are too small that we cannot notice that. Okay. 好，讲中文就是基本上，其实能量是有被切割的，它是有能阶，它不是一个它不是一个连续的。我们的咖啡实际上它看起来是连续的降温，但实际上它其实也是一小个一小个格子这样子阶梯这样子降下来的，只是因为它们的之间的差距太小，间距太小了，我们以为它是连续的。如果今天我们看 microscope 微观的状态下的话，哦，那更是如此。它的 atom 如果要降温，它真的是一阶一阶的降，它是这样跳下来，这样跳下来，而不是连续的这样降下来，这是很重要的一个观念。So let's consider the energy and macro state and micro state. Macro state, macro large scale, micro small scale, state status. All right. So macro state is a configuration we see in the real world. Okay, it specifies the number of the particles in each energy level of the system. Remember that our energy 3/2 nkt, right? It's a summation of all the particles' kinetic energy, right? In the beginning, very beginning of our lecture today, right? We mentioned that. So now here is the same. Macro state configuration is the average or summation of all the particle in the system. So now let's take a look. So now I'm going to introduce the definition of the symbol. M is the total number of the system. So you can imagine that this is summation n j equal to 1 n j. What is j? J is energy level j. So your energy level, you have many energy levels. When your particle occupying such energy level, you have such value of the energy. So your particle will occupy, for example, your particle may occupy here, maybe here, maybe here, and maybe here. Okay, so all the particle may occupy different quantum states, but quantum state may has the same energy. So these two quantum state has the same energy level, and we say that this value of possibility is degeneracy. Degeneracy, GI, well, which means that each energy level has more than one state. So for example, here, the degeneracy is 2. This is 3. This is 4. This is 5. The degeneracy 2, 3, 5. So you can say this energy level has degeneracy, 2 degeneracies. This energy level has 3 degeneracies, and this degeneracy has 5. This energy level has 5 degeneracies. Okay, and you can see that particle may occupy different degeneracy, but may have the same energy. So which means that even they change their configuration, they may have the same energy. Okay, so you can say, of course, here. Let's go back to the. I kind of sort of I forgot to explain. N is the total number of the particle. Of course, if you sum them up, all the particle in each energy level, J, sum it all together, become total number, no problem, right? And then, so macro state is a state that we can see. So, however, it may be achieved by many micro state. although we don't know that. So we see the same macros, we see the same macro state, but actually underneath they may different. They may differ from time to time. Although we see that they're the same, but from time to time they may have different micro states. Maybe they just change inside the energy level with different degeneracy, just changing the degeneracy. But we cannot see that happen in the macro state. So the question is that how many micro states give us the macro state we see that in the real world? OK， 好，我要讲的就是巨观跟微观的状态。那巨观的状态就是我们看到的，那微观的状态是我们看不到的。那当然，微观的状态会决定它的巨观的状态。那这边要解释一下，符号的意义。就例如说 n， 这个 n 就是全部的颗粒的数量。那怎么算呢？就是把每一个能阶上的颗粒数加总起来，就是全部的数量。这当然是没错啦，哈。1到 n 有 n 个 n 阶的话，就从第一阶加到第 n 阶，全部加起来就会是全部的 particle 的数量。好，那这时候我要跟大家介绍 quantum state。那能阶有可能由不同的 quantum state 达成。例如说，这里有2个 quantum state， 有2个量子的状态，只要 particle 跑到这边去，它就是这样这里的 quantum state 嘛。然后它的这个值会有同样的能量，同样的 quantum state 可能会有同样的能量哦。不同的 energy level 可能会有不同的quantum state 的数量，这个数量我们叫它 degeneracy， 也就是说，这个一样的 energy level 它可能会有2种状态可以达成，这一样的 energy level 可能会有3种状态可以达成，这叫做 degeneracy。好，那也就是说 particle 在这些 quantum state 那边选来选去，如果他们今天没有跳到别的 energy level 的话，其实我们在现实生活中看不出来的。好，也就是说，同样的 macro state， 同样的能量状态，实际上它可以被不同的微小状态所达成。那我们就想要知道有几种可能性。为什么要跟几种可能性有关？等一下我们就会知道了。Okay, so now we are going to see how many microstates can achieve the macro state we see in the real world. So let's consider thermodynamic probability. Thermodynamic probability is a really bad name because it's actually the definition of W is the number of the microstates leading to a given microstate, which means that the number of ways in which a given configuration can be achieved. Okay, so this could be 0 to infinity. It's unnormalized. Okay. Right. Thermodynamic probability is a number rather than a probability. So the true probability is actually Pk equal to Wk divided by omega, where omega is sigma k w k. And here I didn't specify the number, which means that to the end, as many as possible. Okay, so the true probability is also a normalized probability. Okay, so it should be 0 to 1. OK， So now, yeah, you can understand what I'm talking about, right? 好，讲中文。热力学几率是一个很烂的名字，它 W 它实际上不是几率，它是数量哦，它是数量，也就是说，它有几种方式去达到现有的你看到的巨观现象，它有几种方式。那这可以是零种到无穷大种啊，所以它是没有被正规化的一个数字 WK。那 K 的话就是这个 K 什么意思呢？就是你有几个现实生活中看得到的现象这样子。好，那 true probability 就是 normalized 的，也就是真正的几率啦。你看到的几率就是 P， 那也就是 WK 除以它的 omega。omega 当然就是它全部总 total 的加总起来嘛，哦的那个 number 加总起来，所以就是这样。我相信你应该看得懂。所以到最后它的值就是0到1之间，没有问题。Now let's introducing a really simple example: coin tossing problem. Coin tossing problem, flipping coin, you can see head and tail. Okay, so yeah, if we have 4 coins, and then you can list all the possible configuration, all the possible microstate, and the final result. Final result. Okay, so for example, N1, N1 may be the number of head, N2 is the number of tail. So you see level, the label 1, 2, 3, 4. So this is all the possible way for the macro state. So this example can let you know what is W, P, and macro state means. Okay. So the first condition is that hey. So 4 N1. Okay, N2 becomes 0. So only probability only 1. You see, this is a number. It's not probability. This is 1. Only one way to achieve that. How about 3 head, 1 tail? It could be head, tail, head, tail, head, tail, head, tail, head. All right. So there are 4 ways to achieve that. And again, 2, 2, you get this one, 6 way, 1, 3, another 4 way, 0, 4, tail, 1. Okay. So omega is sigma phi k equal to 1, wk equal to 16. So you have 16 as the omega, the true probability. You can learn that, right? And then how to get the 4 and 6. Of course, we can list all of them and count it. It's a stupid way to do that. We have a smarter way introduced when you learn when you were in the senior high school. 4 factorial, 3 factorial, 1 factorial to get 4, right? So you can have tail and head number. All right. And of course, how to get the 6, 4 factorial, 2 factorial, 2 factorial. So you got 6. So yeah, that's it. When you understand what is the coin tossing problem, you understand the definition of macro state and macro state and micro state and the thermodynamic probability and true probability mean. 要了解刚刚这些 巨观状态、微观状态、热力学几率跟真实几率的定义，其实我们使用丢硬币的实验就可以教你怎么做到了。哦，你有5种可能的状态，然后你把它全部条列出来，你就会发现有几种方式去达成这个状态。然后帮你全部加总起来以后，你再把它除以它的全部的加总几率，得到它的几率这样子。然后呢，这个4跟6啊、1啊怎么来呢？我高中就有学过，对不对哈？就是 C4取3吧，好对哈。然后你就得到4阶除以3阶除以1阶得到4。那这边的话就是4阶除以2阶除以2阶就是6。OK，你应该知道的。Right. So now you understand the definition of that. Now, let's again, let's take a look at a thermodynamic probability. So now, again, the average occupation number, the average number of the head or tail, j equal to 1, or for head, j equal to 2 for tail. What is that? Again, expected value. Okay, expected value. So NJK, the occupation number for K's macro state. Well, you've done that in the previous page, right? The table, one of the table. And then you can see that all the expected value needs to be summed on all the macro state and then their probability. So you see 4 times 1, 3 times 4. I mean, 4 times 1 over 16. 3 times 4 over 16. So this is expected value again. So you expect that you get 2 head in averagely. Okay, in average. Again, I can write it down here. W is equal to C N over N1 equal to, well, sometimes you may see it written in this way. But all you need to do is n factorial divided by n1 factorial n minus n1 factorial. Okay? The name is binomial coefficient. Okay? N factorial divided by n1 factorial n2 factorial. All right? So W max is 6. So you can imagine that this is actually symmetric. You notice that, sorry, 1, 4, 6, 4, 1. It's symmetric. Okay? So when you get the N1, it's actually 1, 4, 6, 4, 1. Okay? So you can get this distribution. All right? 好，刚刚那个表格都已经讲完了哈，所以总之只是把它写得更仔细一点。我们要讲的是期望值 NJ bar。什么是 NJ bar？J 其实就是假设我们的 head 正面是1，反面是2的话呢，那我们就可以算它的期望值。你这样丢出来，你期望值会得到几个头，几个正面，几个反面，大家都知道是2个嘛，对不对哈？好，这就其实就是算出来的。那这边再跟大家介绍 binomial coefficient， 其实就是我们的 C 几取几啦哈，高中教的这个东西。那我们写的更清楚一点，就是 n 阶除以 n1 阶跟 n2 阶。那当然 n2 就是 n 减 n1 嘛哈，这个我相信大家都知道。然后呢 W max 呢，当然就是当它们相等的时候，会得到这个6这个值。你看到14641，它是一个对称的形式。好。Next one. So let's consider the most probable configuration. What does that mean? It means that n equal to 4, 1, 4, 6, 4, 1, right? How about 8? How about 8? It becomes 70. The highest becomes 70. So this is 4 factorial divided by 2 factorial, 2 factorial equal to 6. Now here is a factorial divided by 4. 4 factorial equal to 70. Okay, so you can see that when you tossing 8 coins, the highest probability for this is 70. 70 ways to achieve 4 tails. So now you understand this, right? You definitely understand this. And of course, this is symmetry again. Now, how about n equal to 1,000? 1,000, how many the distribution, what will it look like? So W max equal to 1,000 factorial divided by 500 factorial, 500 factorial. How can we obtain this? We can use natural log W max. Oh, by the way, you can using the calculator, but in the ancient state, we don't have calculator. So ancient mathematician using natural log to help us. Natural log make multiplication become plus and minus, right? So this is natural log of W max become this one. Still difficult, but Sterling is a really good mathematician, smart mathematician that give us a formulation. Natural log n factorial is approximately equal to n natural log n minus n when n is large. Okay, so we can substitute this to log 10 W max equal to log 10 E natural log W max equal to, if we just substitute this, we can get this W max, natural log 10 W max equal to 0.4343 natural log W max, and W max equal to 300. Okay, so you can see that the log 10 W max is 300. The 300 make it back become W max 10 to 300. Wow, that's a really big number. Really, really big number. Okay. 693.15. Okay. Yeah. So if you can imagine that the natural log, this one can using this, and natural log 500 can using this, so you can get 693.15. However, this is natural log, so we transfer this natural log W makes 693.15 into log 10 base, so we can find that this approximately become 300. So this point 10 to 300. Okay, so you see that this is really, really big number, even if the n is 1,000. So n1 and n2 is the one that almost always occurs in the real world. Okay? So even the particle number is 1,000. This is 10 to 300. Such big values. So you can imagine that if we have large amount of atoms, how big it is, right? So which means that every time we solve the systems, they will have their own most probable configuration always occur, almost always. It's difficult for us to see the case that here or here or here. It will never occur. They will never occur. They just occurred at the peak. OK， 好，这边我要讲的就是4个硬币，它会 peak 是6，那8个硬币的话就是70。那我们想象1000个会怎么样？1000个这个值很难哦，是1000阶除以500阶除以500阶，那怎么算呢？我们就用 natural log 来算一下好了。natural log 算一下可以把它写成这样。那这要怎么写呢？还是蛮难的，没关系，这个东西这个阶啊哈，我们可以使用 Stirling approximation， 这个很好用，以后会用到哈，常常会用到。所以呢，我们如果这样子把它带进去的话，当 n 很大的时候，它就可以这样带，它就把1000 natural log 1000减1000就可以得到这个值。然后这边也是可以这样子算，算出来得到是693.15，也就是说 natural log W max 会等于693.15，但这还蛮难算的，我们把它转成10的 base 好不好？我们把它转成10的 base 以后呢，可以得到哦 natural log 10 W max 会是300左右。好，也就是说啊 W max 是10的300次方哎，也就是说光是1000个原子你就会有10的300次方这样子的。然后比别的还要多这么多，比别的状态还要多这么多，那是不是我们可不可以直接讲 N1 等于 N2 几乎是永远都会出现，其他这个几率实在是相对来讲实在是太小了。那这边才1000而已就变这样子，我们的颗粒数在一般的系统里面更是天文数字。那我们可以想象，如果你看到别的状态的几率就会是更小。所以说，我们每次都只会看到最 random 的状态，而不会看到最不 random 的状态。什么叫最不 random 啊？你看这边，这边是 N1 等于 N2 嘛，是很 random 的。有的时候是 N1，有的时候是 head，有时候是 tail，head tail，head tail tail，head tail 很 random。但是如果是这里的话，这边都会几乎都是 head tail，啊 head，或这边是 tail head。所以也就是说啊。这边其他的区域都是不是很标准 order， 所以这跟现实不太像。Okay, so I guess it's time. It's time. Okay, so I will see you next week. If you have any questions, just come here. Thank you.